If you go back just a few decades, these devices were a standard fixture on industrial buildings, warehouses, farm structures, and even residential rooftops across the United States and Australia. But today, if you walk through any new housing development in the country, you will struggle to find a single one. They're called turbine ventilators, or whirlybirds, and they have been proven by independent testing to reduce peak attic temperatures by as much as 37 degrees Fahrenheit and cut cooling costs by nearly 15% without a single watt of electricity or any electronics of any kind. But if they were so great, why did we stop using them? And if they're really as efficient as the test data says, should we bring them back? Let's find out. The idea of moving air through a building without burning fuel or consuming power is one of the oldest engineering solutions in human history. We've already covered the mechanism. Persian architects used to do this multiple times on this channel. Tall masonry wind catchers called badgers, designed to funnel desert breezes down into the lower levels of a building while pulling hot, stale air out through the top. But they weren't the only ones using the air to cool their interior spaces. In the Tang Dynasty, Buddhist monks integrated natural ventilation ducts throughout cave complexes to control temperature and air quality underground. And by the Middle Ages in Europe, air was regarded as one of the 4 essential elements, and the way a building breathed was treated as seriously as the breathing of the people inside it. These were all passive systems, relying on the shape of the building and the direction of the wind to do the work. The push towards something more active began during the Industrial Revolution. Deep mines needed a way to keep workers alive underground, and engineers responded with fire-driven ventilation systems and manually powered wooden fans. By the 18th century, the Houses of Parliament in London had installed a primitive mechanical system called a blowing wheel to replace foul air with fresh air. And by the 19th century, figures like David Boswell Reed were building steam-driven ventilation systems for hospitals and barracks, where the risk of airborne disease made the movement of air a matter of life and death. But all of these systems required fuel, infrastructure, and maintenance. The breakthrough came in 1910, when an engineer named Samuel Ewart patented a design for a spinning cowl that sat on top of a roof and actively pulled air out of the space below it. Ewart's original patent describes the device as a solution for both ventilation and preventing downdrafts in chimneys, the gusts of wind that would blow smoke back into a home. And unlike anything that came before, his device had no fuel source, no electricity, and no human input of any kind. Ewart's creation was simple, yet extremely clever, drawing on 3 separate principles that work together to fix a common problem every house suffers from. During a typical American summer, solar radiation heats the roof surface and turns the attic into a thermal reservoir. Temperatures inside that space can climb past 150 degrees Fahrenheit. And that heat doesn't just sit there. It radiates downward through the ceiling and into the living space below, forcing your air conditioning system to run longer, work harder, and consume more electricity just to maintain the same temperature. According to the U.S. Department of Energy, every degree of attic temperature increase can boost your cooling load by up to 4%. And in many homes, the ductwork that carries cooled air runs directly through that superheated attic space, meaning the air is warming back up before it even reaches the rooms it's supposed to cool. So the entire point of attic ventilation is to break this cycle. Move the hot air out before it has a chance to radiate down. And that is exactly what Ewart's turbine was designed to do, using 3 separate principles working together. The first is Bernoulli's principle. As wind passes across the curved vanes of the turbine head, the air is forced to accelerate, and when air speeds up, its pressure drops. This creates a zone of low pressure inside the turbine that generates a suction effect, actively pulling warm air upward from the attic and exhausting it outside. The key point here is that, unlike a static vent, which just sits there and relies on air drifting out on its own, the turbine ventilator uses the kinetic energy of the wind to drag air out of the building. And the faster the wind blows, the harder the turbine works. But here's what most people don't realize. The turbine doesn't stop working when the wind dies down. You see, it also leverages something called the stack effect, which is the natural tendency of warm air to rise. Warm air is less dense than cool air. So, in a building with soffit vents at the eaves and a turbine at the ridge, that rising warm air creates a gentle pressure gradient that pushes air up and out through the turbine, even when it isn't spinning. The third principle is the Venturi effect. As air is squeezed through the narrow gaps between the spinning vanes, its velocity increases, which further reduces pressure inside the turbine housing and accelerates the exhaust cycle. All three of these effects compound one another. The result is a device that generates continuous negative pressure at the highest point of the building, pulling hot, humid, stale air out and replacing it with cooler air drawn in through the soffits below. And this simple design has been proven to be remarkably effective. A study by the Air Infiltration and Ventilation Center found that installing a turbine ventilator increased attic ventilation rates by an average of 15% over a full year, with improvements of up to 50% when the wind hit the unit from its optimal direction. And data collected in the San Diego area showed that a properly installed turbine system reduced peak attic temperatures by as much as 37 degrees Fahrenheit, which translated to an average energy bill reduction of 14.6%. To put that in practical terms, a standard 12-inch turbine moves between 250 and 350 cubic feet of air per minute at just 5 miles per hour of wind. A 14-inch unit pushes that to between 350 and 500 cubic feet per minute. And because the device consumes zero electricity, every dollar of cooling savings is a pure gain. But these numbers come with an important caveat and are part of the reason why turbine ventilators have begun to become increasingly less common sights in the United States, along with the rest of the world. A study from Deakin University found that while a single 12-inch turbine could achieve a flow rate of approximately 150 cubic feet per minute, the resulting air velocity inside the roof space was only about a third of a foot per second. In ventilation terms, that is technically classified as still air. Their conclusion was that a single turbine is often not enough for the thermal loads of a modern home. And this is where proper sizing becomes critical. Most building codes recommend 1 square foot of ventilation for every 300 square feet of attic floor space. But in hot, humid climates like Florida or Texas, many professionals recommend doubling that ratio. But the performance limitations of a single unit are only one piece of the story. The most problematic was mechanical failure. The defining feature of the turbine, its spinning head, is also its primary point of failure. Over time, the ball bearings can degrade due to moisture, dust, or insufficient lubrication, producing a squeaking or grinding noise that transmits through the roof structure and into the living space below. Cheaply manufactured units are especially prone to this, which, over the years, has given the turbine a reputation as noisy and unreliable hardware. And there's a more subtle engineering problem called short-circuiting. This occurs when a turbine and a ridge vent are installed on the same roof above a common attic space. Because the turbine pulls air more aggressively, the ridge vent can actually reverse its function and start drawing outside air in, bringing rain and snow with it instead of exhausting warm air. For this reason, most roofing professionals recommend choosing one exhaust system and sticking with it. And because ridge vents are easier to install, the turbine is usually the one that gets dropped. But beyond the engineering, there is the issue of appearance. Turbine ventilators are highly visible from the street, and in the American housing market, curb appeal drives value. Ridge vents, by comparison, are shingle-over designs that are nearly invisible from ground level. Homeowners associations across the country have frequently restricted or outright prohibited turbine ventilators because they disrupt the clean, uniform roof lines of modern suburban developments. And even in Florida, where state law protects energy-saving devices, many homeowners associations have worked around this by requiring turbines to be placed on the rear slope of the roof only, which may not align with the prevailing wind direction, reducing their effectiveness entirely. Building codes have also made it more difficult to implement turbine ventilation. As American homes have become tighter and more energy efficient, codes like the International Energy Conservation Code and California's Title 24 have begun mandating mechanical ventilation systems that can guarantee precise air exchange rates. Because a passive turbine's performance depends on wind speed and temperature, variables no one can control, it falls into a regulatory gray area. So, the real question we should be asking now is whether we should all be using the turbine ventilation system. And the honest answer depends entirely on where you live and what you're trying to accomplish. If you are in a hot, windy climate, the Gulf Coast, the American Southwest, or large parts of the Sun Belt, a turbine ventilator remains one of the most cost-effective ways to reduce your cooling load. A single 12-inch unit costs between $20 and $100 for materials. Professional installation adds between $100 and $300 per unit, depending on roof, pitch, and complexity. For a standard 1,500 square foot attic, 2 units is generally sufficient, and in a southern climate, the energy savings can pay for the installation within 3 to 5 years. And because proper attic ventilation prevents shingles from overheating and the roof deck from trapping moisture, the device can extend the lifespan of your roof by several years. But in cold climates or in homes with modern high-performance building envelopes, a turbine is probably not a suitable choice. In winter, internal moisture can freeze the vanes solid, shutting the system down at the worst possible time. And in an airtight home, where mechanical ventilation is already managing air exchange, adding a passive exhaust point can disrupt the pressure balance the system was engineered to maintain. In reality, for most homeowners, particularly those building new or re-roofing, a ridge vent is probably the more practical choice. A full-length ridge vent running the span of a standard roof provides over 900 square inches of net-free ventilation area, which is roughly double what 3 14-inch turbines would deliver. And because the ventilation is distributed evenly along the entire ridge rather than concentrated at 2 or 3 points, it eliminates the dead zones that turbines can create in the corners of an attic. There are no moving parts, no bearings to fail, no noise complaints, and no homeowners association letters. It just sits there and works, year after year. If you liked this video and enjoy learning how to become more self-sufficient and energy independent, then subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. And if you want to see how these same principles of thermal buoyancy can cool an entire home without any electricity at all, then you need to watch our video on the solar chimney right here.